So we are immediately jumping to the next presentation, which is given by Ricardo Reis. Let me introduce him briefly. Mr. Reis received the PhD degree in microelectronics from the National Polytechnic Institute of Grenoble in France in 1983, having Professor François Anceau as advisor. Doctor honoris causa by the University of Montpellier in 2016. He is full professor at the Informatics Institute of Federal University of Rio Grande do Sul, Porto Alegre, Brazil, a member of IEEE CAS Board of Governors and IEEE SIDA Board of Governors, member of IEEE IoT Initiative Activity Board, chair of the IEEE CAS SIG, and on the IoT IFIP Fellow Award 2011, 2021, 2022, ACM, ISPD Lifetime Achievement Award. Please, Ricardo.
Thank you very much. So it's a great pleasure to be here today. So I'm going to speak in my bad English, but when in the testimonial session that will be the last session today, Suzin, Navo, and Claudio Walter asked me if they could speak in French. I told them that they should speak in English. So to cope with this, I will use my English. Besides that, would be great also to speak in French. No? So as you can see in this first slides here, you can already see some circuits, so that we had the opportunity to do the photos a long time ago. Some of them were rescanned a few time ago to present, to submit them to the DAC, the art show. So some photos that were done here and some others, as well some views of some visualization of algorithms that I'm going to show by the end. Also, some of them were presented at Design Automation Conference. So there is a long history on all this. So as you saw, my talk is expected to be a technical one, but before going to the talk itself, some small preface. So about the reverse engineering of the Z8000. So in reality, I could do a full talk about this because this was a great experience. So I took the photo with the Polaroid at that time, and then we mounted the poster that probably now is at, so Gio told me that it's a Connie, so I would like to have a photo of the full that I don't have. But so it was, I learned a lot of things that we cannot find in the books, because doing the reverse engineer, I was able to first to recognize the transistors, then to recognize the connection between transistors, then recognize the logic functions, and then to see how they have done the placement of these gates. So it was NMOS technology. So NMOS technology, as you know, have just one gate, one transistor between the output and the VDD. So that was a depletion gate. And then it was able to do large functions because we don't have the problem with CMOS that we needed to have the same amount of transistors from the output to VDD, then from output to the ground. So this limit the number of inputs that we can have now in CMOS cells. But with NMOS, we were able to have a large one. So in the Z8000, there was some gates with more than 23 inputs. And sometimes it was interesting because one large gate we were able to was placed in one location and part of the gate in another location. So this is just an example of kind of things that we're able to see. So as it's written here also, the control part, the idea that Zilog used that time, the observation, let's say, was the same that gave origin to the RISC microprocessor, reduction instruction set But in the RISC microprocessors, the idea was to reduce the number of instructions, because reducing the number of instructions, the control part will be smaller and then it will be faster. And this was done for a long time. And in reality, together with the development of the RISC architecture, there was also the increase on the possibility to have large words, that was also more orthogonal, the decoding of the instructions and so on. But here in this 8000, they have done the same observation. What was the average use of each machine instruction? And then there was 4 of them that was the top seller, so in the top of the billboard of the use of the instructions. And then they construct a specific control part to take care of this for instruction. And as it was only for instruction, it was small and then very fast. And then the speed of this 8000 at the time was really nice compared to other solutions. But this is just some brief comments about this reverse engineering. So doing the photo, the poster, I use a tape to define the code for each transistor. And then I was able to build all these connections between transistors and so on. So these tapes were not flat like you are seeing here. I put in such a way that they were in 90 degrees to the photo, to not forbidden to see what was behind of this label. No? And then probably there is still the report of the DA that was in the scope that I have done this reverse engineering in the library here. No? So with the gates and so on. And then I was possible to see how it was the division of the state machine, all levels of timing of the circuit. And there was some large strips between VDD and ground because there was the buses with all these signals of timing that were being mixed with the signals that come from the decoding. And decoding that time in the Z8000, it was a kind of PLA, but only the first matrix was a PLA. The second matrix was just a mapping of the logical functions in a set of normal gates. So it was very, very compact. And also seeing the density of the circuit at that time, it comes the idea that we should think about doing some automation, the layout design, trying to have the same density. So, but till nowadays, we don't have commercial tools that can provide the same density as these designs that were done at that time. And the Z8000, for example, all the control part, it was designed by hand. So the computer was just input of rectangles designed by hand. And maybe this is the reason that the Z80,000 never appears, because the work was too big to arrive to a solution. Also here, the first paper I have published was in '82 in Adelaide, in Australia. So I had the opportunity there to meet all these people here. And I have done something that, my ignorance in how to prepare a paper and to present that time, that I prepared the paper, I submit without talking with Anso. I only talked with him after the paper was accepted. And also, I didn't put his name on the paper, no. So I was not aware of the procedure that normally we do nowadays. And so nowadays, a student don't send a paper without talking with the advisor before. No? And then when I told him that it was accepted, he just told me he didn't do any comment about this my procedure, but he told me that it was expensive to go to Australia. Then as I went to cruise and I find a cheap ticket to go by London, the organization of the conference in Australia gave me $500. And also one of the professors of the organization told me that I could stay in his home. So the cost finally was small, and then also say, okay. But what is interesting, in fact, is that just after I realized that Anso was an invited speaker in the conference. So I was not aware of that when I submitted the paper neither. And then 1 week before the conference, he called me in his office and he told me that he was not able to go to present his invited talk. And then he gave me the box with the slides. He just gave me the box and so do you present on behalf of me the invited talk? Okay. So my first conference, I presented my paper and also the invited talk of François Anso. So this was a great demonstration of trust from him to allow a younger PhD student to present his invited talk, and together with all these people here. By the way, as I was presenting his invited paper, I was also invited to the small social events with these invited speakers that you are seeing here, the name. So, okay, so this is some small history. And then also the same year, well, there is more history that I don't have time here to tell you that there was another paper also the same year as ICCC in New York. And then we have done together this one that was related to my thesis subject, but so the first paper in Solid State Secret Journal in '82. So this was my first paper in a journal. And you can see in the top on the right a small figure that this was a strategy that we defined observing the Z8000. No? Because all the connections in the Z8000, besides it was only a NMOS with one metal layer, the connections were over the gates. At that time, the first standard cell circuits had a row of cells, then a row only with connections between the other rows of cells. So there is a large space wasted only with connections. So we developed this approach, then we keep working on it when we returned to Brazil. And then Marcelo Lubaszewski, that went here later to do a PhD with Bernard Courtois. So he has done the master with me, working in a tool to automate this kind of procedure to do the layout synthesis. Well, so this is some comments. If some of you go to the FETCH conference next Thursday, I will talk a little bit more about this experience and how it brings us to keep working on layout of automatic synthesis. No? So I could divide now the talk in two parts. The first one is just one slide. So this is a trend without return. And I think that still now many people don't know it. When you talk with some people who work on embedded system, for them embedded system is just to programming a platform. But this is it's okay for some problems, no? But if you want to optimize, that is something that I will try to stress more here. We need to go to a specific and dedicated chip to have a real optimization on power, the delay, and so on. So now the second part of the talk. So if you see the Internet of Things world nowadays, each year more and more devices connected to internet, so it's exploding the number of. And what means all this explosion of device connected to internet? More need of power. So to cope with this, I think that we need to change some of the traditional physical design approach. So if you see here the number of transistors produced in the world in till 2017, so I took this picture from Semiconductor Industry Association till 2003, then I got the other numbers. So if you compare from 2014 to 2017, in just 3 years, the number of transistors produced in the world was 4 times more. So from 250 quintillions to 1 sextillion. And for this year, 2022, the estimation is about 8 sextillion just in 1 year. So about the half of the transistor produced from 47, that were very few ones, till 2018. So this is, so till where we can go with this increase in the production of transistors. The point is not to have more transistors, but the energy to run them. So also another point is that everybody knows that the investment in education, science, technology that is fundamental for the industry nowadays is not only for the industry on electronics or microelectronics or in computing, but a large set of other sectors like agribusiness, healthcare, and transportation depends more and more of the development of the micro and nanoelectronics now. So as I was talking before, the embedded systems, so we consider that more and more the embedded systems, as we need a reduction on power optimization, demands to do dedicated embedded system. So dedicated chips. So this idea that in some locations nowadays is being used that we can use any microprocessor and so on to solve everything. We can solve a lot of things, but it's not an optimized solution. No? So to have optimized solution, we have to do power optimization, all levels of abstraction. So here comes on also this speech of and so of hierarchy, no, to take care of this. So then we think that application-specific embedded system is the future for a lot of applications. So another data here is about the cost and the amount of transistor we can find in some devices. No? So this data from now almost 12 years. No? So a grain of rice had at the time the price of more than 125,000 transistors. So they bought a package of rice in a supermarket in California. And also they went to a electronics store in front of the supermarket. They bought a chip. And then this is the count. So we can consider that the transistor is cheap or that the rice is expensive. But the main point here is that even if you consider that transistor is cheap, the energy is expensive. So this is the main reason to consider to do an optimization of the power. Also, another point, so is that low power is related to reliability. So everyone that works on reliability knows that if the chips use more energy, the lifetime can go down. No? So why optimization is a keyword in nano CMOS and so on, for sure is that more and more we have these embedded systems that require low power. No? So modern design needs optimization. So this is the keyword that I'm saying. So how many plants also will need to cope with the IoT, IoE world? there is no way. There is a lot of forecasts saying that we are not going to have energy to run all electronic and computing systems if you keep doing the designs as it's being done nowadays. For sure, also there is other things related to. So it's interesting that in USA, there is a nice talk by Patrick Greneveld about the energy used to go from one location to another location, walking, using bike, using a tramway. Well, I like a lot tramway, but I don't have in Porto Alegre yet. There is in Rio, if you want now. But there is a company near Porto Alegre that is starting to produce the tram. Let's see. So airplane and so on, and then the electric cars. So the conclusion is that electric cars, green or no, depend where. No? So we have a lot of electric cars in USA, but the production of energy in USA is not a green production of energy. In Brazil, it's mainly green. So it's the hydraulic plants, and now the second source of energy is the eolic, and so on. But we don't have many electric cars now. It's mainly run with mixed motor, gasoline, and ethanol. But as you saw also, the power consumption drives the more evolution since a long time. So this move from NMOS to CMOS, so it was already talked today, that, and so was also thinking at that time that when the microprocessors were still using NMOS, that they should change to CMOS. And if you see the whole flow, so we have the main flow that is the synthesis one, but it's more and more important, the verification flow also, and it's becoming also very important, the estimation tools for each level of abstraction. So this can be fundamental for decisions in the whole synthesis process. And also, we need more and more optimization tools to work in each level of abstraction. And then the optimization tool means what? We have one description using one language, one level of abstraction, and then we do an optimization of this description, and then the output is another output using the same language, but optimized description. So then power optimization must be done in all levels of abstractions, and for this we need these power estimation tools. Also, another problem that we have to take care is the power wall. So there is some examples of the industry that when they reach the silicon, doesn't work because it was expending much more power than it was possible to dissipate. So another point. This is a view of the power being dissipated in each region of the four plane of a circuit. So I think this is interesting because it brings a point that all the placement and routing tools, they only care about the position and the routing to avoid the congestion of the connections and so on. But nowadays, we have also to consider the power dissipation in the whole four plane. So here you are seeing these red parts of the layout. So this is not good. So that means that this placement must be redone to distribute this power consumption. So there is more factors that are needed to be considered nowadays when we are doing the placement and the routing of the circuit. And routing is a major issue nowadays. If you talk with people that are designing the top AMD processors, Intel, and so on, they always have the same speech that the design of the connections is the most crucial point in the design of the circuit. So another point that is not a trend, but a reality is the use of hardware accelerators. And with this come also the concept of dark silicon. So if you see this Apple chip here, all the blue blocks they are hardware accelerators. What means this? I don't think the name was the best one, but this is the name that's being used. That each block in this Apple 8, there was 29 of these hard accelerators. One for sure that we find nowadays in each system on chip is for cryptography. So the use of software for cryptography is something from the old past. We don't need to use the CPU, GPU to do the decoding and coding of the instructions, because which data we need to do encryption or decryption? The data that is arriving to the chip or going out of the chip. So we have a module, a hard accelerator dedicated to cryptography, connect to the output and input pins. That's all. It works in parallel to the real work that the CPU and GPU must do. So this is just one example. So there is a hard accelerator for filters and so on. We don't know what are the old 29 that Apple was using in this chip, but no. So then this concept of dark silicon that is very important to do power optimization, that the hardware accelerators that are not being used, they are shut down. So only the ones that are being used at this moment. So this is a great procedure to reduce power consumption. But what we are going to talk now is that even using this, it's important that the hardware accelerators that are working, they also should be optimized, because when they are working, they are expending energy. So we need to consider this also. So this is just another Apple processor. Now they are all multi-processor system on chip. Here we're also introducing the neural processing unit that is responsible to recognize the face of the user in a cell phone. I'm going to try to speed up a little bit. So when we see this kind of new Apple microprocessor nowadays, here we could go in more detail and to see that all this vision of hierarchy that was talked this morning also is fundamental to cope with the design of this so big processor. So hierarchy here is very important. By the way, my thesis here was in foreplanning. So this was also something that is fundamental to design any chip, because several blocks are designed by groups with the specialization in the block, and they needed to communicate between them. I remember a long time ago when Intel was doing the design of the 486. I visited Intel, and there was I think 4 or 5 meter plotting with the design of each block. Some blocks were already ready, so they were fixed in this foreplanning. Then the people that were working the other block, they were able to see if there was still an extra space or no. So this was an important communication between the groups that were designing each functional block of the microprocessor. And this is, for sure, nowadays they don't put more in the wall, but in the computer, but this is fundamental to take care of this hierarchy of the chip and to have a good foreplanning. So the energy harvesting is another important point nowadays. You can see more and more chips being implanted in people. So using this, we should avoid to have an extra surgery to change the battery. So this is very low energy. So as you can see till now, in a large set of applications, the power reduction is more and more fundamental. Medical applications for sure. So another point is that when we have a smaller power, and also relates to this, we have a smaller VDD, the circuit becomes more sensible. and becomes also more sensible to the radiation effects that reach us here in the ground. So then we should also consider the reliability of all these chips for this kind of applications. For sure, for transport, we cannot have any accident. So both things. Also to the agribusiness, more and more we have this smart farm and so on that demands dedicated chips. One reason also is because in this kind of smart farm, the number of chips that is requested is really huge. No? Imagine a large farm, how many chips they need to control everything. So some reliability issues also. Now, the circuits should be designed to consider, to be aware for internal and external noise. If somebody, when he's sleeping, that produces some noise, this should not affect the circuit, no, for sure. Aging, more and more an important aspect, variability, radiation effects, and so on. So about variability, that we consider that variability and power are the two main problems in nano-CMOS. So if you see this variability written in yellow and green, can you see a difference, another difference between them? There is a small difference in the size of the font. Maybe it's not so clear only this one, but if you put several ones in the same picture, now it's more clear that the green one is a little bit smaller. Then we can reduce the fonts of everything. Now it's much more clear that the green one is much smaller than the yellow one. But in both cases, there is a change of only 4 points. So the absolute change on the variability in both is the same. But for sure, in the second case, the percentage of variability is very big. So this is what is happening nowadays. So when you put some bore or some phosphor in the chip, maybe the variation is more or less the same than before, but consider the quantity and the size of the stuff, the relative importance is much bigger. So this is another point. So this is a wafer that was being processed by Infineon in Munich. So a former PhD student of mine, he has done an internship there, and then he has designed some circuits to verify the variability. So the circuits were fabricated in the wafer. Then it was 3 wafers. That time it was still 130 nanometers and 90 nanometers. And then you can see in this graph, considering here the frequency on the z-axis, no, there is a big change in the whole wafer, no, depending on the location where the circuits were. No. So there is a lot of data about this that are in this book. So power reduction, another one point that is clear for everybody nowadays is that the leakage current, so the static power, is sometimes even bigger than the dynamic power. And the static power is related to the number of transistors. That's why we consider it's important to optimize the number of transistors. And nowadays, most of circuits are using much more transistors than is needed. So the goal of one of our projects to reduce this number of transistors. And doing this, we are also reducing the number of connections. So then it will be easier to do the routing. And so this is mainly in consequence of the using of standard cell design. So because the libraries don't have many functions. No? If you see this graph that was published a long time ago in ICCAD by that, if you consider the 4 stacked NMOS transistor and 4 PMOS, we can have 3,503 different functions. How many different functions we find in a commercial cell library nowadays? 50, 70, not more than 100. No. it's nothing to do with the cell library that we can have by the end of a design of microprocessor, because when they design a microprocessor, they don't use a already done cell library. No? They start doing all the cells that they need. It's a very competitive sector. No? Then they have a larger library that is available by the end of the design of the processor, 3-4 years, depending on the time they take. But it's also possible sometimes to have even 5 NMOS stack transistors. And then, considering 5 NMOS and 4 PMOS, we can have more than 28,000 different functions. So the space of engineering to do optimization is much bigger than using the cell libraries that we have nowadays. And nowadays, there is a step that you know as technology mapping, that we have to change the equations to cope with the cells available in the library. So this is a desoptimization step. And maybe some people can say, well, you cannot have 5 stacked NMOS transistor. Well, I saw some examples. I don't know if you remember a company name was Zenasis. So they took standard cell designs and they saw the critical parts, and then they changed a set of basic cells to a more complex one. And they have some examples that even using 5 serial transistors, the total energy and the total delay was smaller than the set of small gates that this super gate was taking the place. And when we compare this, we have to compare not only the delay in each basic cell, but also in the connections between them. And as you know, the delay in the connections nowadays is more important than the connections in the gates. So here is a small example, a very small equation with 4 gates, using 14 transistors. So if you change this equation a little to implement it by just 1 gate, like here, we reduce from 14 to 8 transistors. That means we are reducing static power in the same amount, but also we are eliminating the connections between the gates. That means that we don't need to take these connections to the metal layer that will demand also some vias. And vias, you know, that is a forbidden region to do connections. So everything goes in the good direction. The point is that we need a specific flow for the synthesis and also for the characterization. And then what we think is that we need to change the approach to do the physical design, as less transistor means less leakage power. And then also less transistor means less connections. And well, this is another book with some examples on this, and also showing that having less connections, we are also working to increase the reliability. You have more space for sure. Then power and the reliability, they are things that are connected, related. And here is a little bit of the history. So starting from the reverse engineering of the Z8000, where the control part was done using random logic. Then the 68000, which reverse engineering was also done here. Then it was a principle of automation by using ROM and PLAs. And the control part had two levels of ROM, micro and non-ROM. And then Intel later started with standard cell-like. As I told you, the microprocessor is not a standard cell in the sense that they are using cells from a library, but they are constructing a library during the design. And then we think that it's moment to return to the lessons that we can observe in the old circuits that were designed by hand, using again the design with random logic, but doing them automatically. So here an example of the photo of the Z8000 that it was taken at that time here in Grenoble. So I think you should agree with me that you cannot see empty spaces here, no? So the engineering of the layout of this circuit was quite good. Even that time there was only one metal layer, so much more complicated to do the routing than some routing we're using polysilicon in the vertical. There was also the possibility to do 24-degree lines also, that nowadays is avoided. So this is for sure, we have to consider that now the design rules have much more restrictions than before now, but this is a complication in one hand, but it's also easier in another hand because you cannot have a so large set of how to design a transistor. No? So the layout strategy to do the design automation, so we have to consider transistor topology, the management of the routing in all layers, the VCC and ground distribution, clock distribution, contacts and via management, body ties management, transistor size and folding. So each decision in each one of these topics affects the other. So if you do a tool that can consider everything, the problem is the running time. So we have to find some tricks, some ways to have the possibility to have a good solution, but in a shorter time. So we think that it's time to do the physical design not as a place and route of cells from a library, but if you want optimization for sure, but doing the design of a network of transistors. So place and routing of transistor doing any combination. So here is the layout that we're doing automatically by one of the tools that we're developing in Porto Alegre. Another example. So all these layouts were done in a completely automatic way. Here is a vision of one of them using importing to the Cadence tools. And here is an example of a small multiplier carry save 4x4. In the top was using a vendor tool and the button, our solution. You can see here that there was a nice reduction in number of cells because doing the automatic design, we use more complex ones. But the main point is the reduction in the number of transistors. And this was the main reason for the reduction on the power, due mainly to the reduction of the static power. But for sure, there was also reduction in area and delay. So something that we can also play a little bit is to have multiple layouts when we are doing automatically. We have this possibility to have multiple layouts for the same function. And this is interesting if you want to complicate the life of people that are still willing to do reverse engineering, because they will see different layouts for the same one. Another point that in most cases people don't care is about the transistor arrangement or transistor reordering. So if you see here this pull-up network, the transistor A in the first option, the top is close to the output. In the second one is close to VDD. No logic difference at all. But when we see more in detail, the sensitive nodes for the radiation effects, for example, or any transient, are different. So if you want to consider this aspect, we have also to see which is the best transistor arrangement for this. Here is the same logic function with 4 solutions. So for sure, one of them is the best one, considering the sensitive to radiation. Okay, and then you can see here that even the size of the cell is quite different. And another point also is that, we could discuss a lot of things about this, but so to consider all these different options, we need to have this possibility to have an automatic layout design. So I'm going to skip some slides. So cyber physical that now is using not only electronic elements, but mechanical, organic, and so on. Reconfigurable architectures also, that is another topic to discuss about. 3D circuits. So we have the traditional 3D circuits with already traditional with DSVs, where you can have each layer or each tier using even different process dedicated to different type of circuits. And also nowadays a nice work related to monolithic 3D So here at CIT, there is nice works about this. No? And where the second layer of transistor is not another chip that is placed over the first one, but it's a deposition of new transistor, and then the monolithic vias are much smaller than the TSVs. So also I'm going to skip here that you have different types of monolithic 3D. Also all these aspects to tolerance to radiation effects. Just a curiosity, by the way, where I live in the south of Brazil is a region for the South Atlantic anomaly. And then you can consider that we are more affected by the radiation. In fact, it's not the region that are more affected by radiation are the poles. No? But there is this, and this is a nanosatellite that was sent to the space about 8 years now. There is 2 chips inside. One designed in our university. Fernanda Casten-Smith was the leader of this design. And the Federal University of Santa Maria, that is about 300 kilometers from Porto Alegre. And then it was expected that this was going to work for 2 years. But 1 year and something later, during 1 week, no signal from the space. Then later on, we realized that this week was a week with a stronger solar activity. And then after that, the circuit was recovered and is still working till now. So each time it crossed the top of, in our state, antenna in the University of Santa Maria catch the signals. Another aspect also that we don't have time to go in details about electromigration. So the position of each output in the metal layer that is related to the output changed the lifetime of the circuit. So in this book, there is much more details about this. Quantum circuits, well, Nani talked about it this morning. So, and visualization tools that we consider that are more and more important for 2 things. One is to help designers to see what is happening when they are using some tools, and also for the ones that are developing the tools to see how the tool is working. If you see in this picture in the top, there is the application of 4 traditional placement tools. And you see that by the colors of each block that the result is completely different. Here is same algorithm, but with different parameters. You see that the evolution of the placement is different. Then we can see what is going on. Here is another one. And another point that is important, that nowadays the blocks are not more rectangles, the functional blocks. So the tools don't care about this. They try to put the cell that should be placed near to the other. No? So here is another one for about 200,000 cells, means about 1 million transistors. So this is the placement result using the tools that were developed in our university. Here is a placement. The placement, all the cells are in the middle, in the beginning. Then the algorithm, and then we can see how the tool is working. And this visualization was really used in the development of some tools that were developed by our group in the university. This is also another one using cell clustering. And I'm going to skip this. So concluding, I see design depends more and more on the quality of the tools. And we need more and more dedicated chips to have low power chips. And a way to reduce power consumption is to reduce the number of transistors. And optimization is for us the key word in all this process if you want really to optimize the power. But when we are optimizing power, as I told you, reducing the number of transistors, optimizing connections, also delay and things like that. And so EDA is a game, useful game. And then this is the main keyword. But just something else. So these are the some students that I had the opportunity to be advisor. So they are grandsons of Anso. I didn't put here the grandsons that are the ones that were advised by the ones that were advised by me. So there is a long, but just to give a flavor of where they are now. So we have people in many locations around the world. If you want to see more photos that I have done in the past, in this Facebook page is there. If you want to see the talks organized each Friday, 1:30 p.m. Brasilia time. And this is the last slide. So this is the genealogy of scientific genealogy. So Anso, his advisor was Luis Bollier, no? Then Jean Kustman, and so on. And you see that going in the past, in the top, it goes by Lagrange. Lagrange at that time had no idea that, yeah, this is the last one. Yeah. Yeah. And then it goes to Richard Newton. So that's it.
Thank you very much, Ricardo. Okay, let's jump immediately to the next speaker. So this is, where I am, yeah. So this is Manfred Glesner from the Technical University of Darmstadt in Germany. He's going to speak about from the first MPC activities of François Anso toward the ubiquitous open science hardware, a status overview. So this presentation is online. So I don't know if Manfred, you can speak and introduce yourself because we didn't receive your bio. Can you please take over?
Hello, my name is Manfred Glesner, and I'm a professor emeritus from Darmstadt University of Technology. And it's my great pleasure to participate today in your François Anso Day, remembering the founder of microelectronic system design of MPC activities at your university in INPG in Grenoble. So the title of my talk is from the first MPC activities created by François Anso towards what we call nowadays ubiquitous open science hardware, and we will give a status overview. When we look back to these old times, I remember we met often François Anso on meetings we had in Grenoble. I was participating in the MPC conferences you were holding every year in different towns of France, and I remember his participation in international seminars like in Bristol around 1982 or 3, and giving some remembering to Anso. I remember that after my talk on a French MPC meeting in Bordeaux, he came to me and said, I'm angry on you because I know you are speaking an excellent French, and why did you give your talk in English? So, and he also did not like when I participated in a PhD examination that I used English for questioning the candidate. François Anso had his colleagues in the world. In Darmstadt, we had on a similar age and similar activities Professor Robert Piloty. Robert Piloty worked at the Technische Universität Darmstadt from 1960, from 1964 to 1990 when he retired, and Robert Piloty is one of the pioneers in computer architecture. He helped to create on the federal level of Germany the discipline in computer science, and he was vice president of the International Federation for Information Processing, which is, and he represented the German computer science in the world. You all are aware that we are living in complicated times. So at the beginning of my talk, I want to show you this transparency here, that humanity is in a complicated situation. And here we have on the left side mentioned the top 10 problems for humanity. You see here the 10 topics we have to fight with as problems for humanity. We have here on the first three places energy, water, and food. We are all aware about the gas discussions, the oil discussions we have, for example, with Russia at the moment. So the times are really very complicated. Poverty, terrorism, and war, disease, that are all very important topics. Talking now about the topic of MPCs, in the old times, the people from semiconductor technology, they were working also on the circuit design topics, because at that time the circuit complexity of the integrated circuits was quite low, and it was not a difficult matter to develop the technology and creating also at the same time applications in form of digital logic or analog integrated circuits. There was a famous journal with the name Electronics in the times, and in its October 1981 edition, they gave an award for his achievements to create a common design culture for the LSI area. And this distinction was, this prize for achievements was given to Lynn Conway and Carver Mead. Both are still active nowadays in our field. In recent time, Lynn Conway got a lot of appreciation from international societies for her work, and Carver Mead, we will hear him giving a memorial speech for François Anceau. So they invented a new design culture, and that means they at that time they used the Hewlett-Packard semiconductor technology facilities for creating the circuits for their first MPC 79 design course. So we see here the results of this first run. And on the upper left, we see that with the help of an E-beam, it was possible to write on one wafer, and this wafer was certainly something between 3 and 5 inches. You could write several designs from several student groups, and when you look to the individual designs that is shown here on the right side, you can write with an E-beam several multi-projects on such a chip, and you are bonding only the design of a specific group, and you can give from the mass of fabricated circuits the specifically wired integrated circuits to a certain user group. This idea of a multi-project chip was initially not favored very much from the technology group, but nowadays it is common practice in the world. Also, Carver Mead and Lynn Conway, they published their experience of the first MPC run in this booklet on MPC Adventures, a publication from Xerox Palo Alto Research Center. And in addition, the two people, Carver Mead and Lynn Conway, they wrote a book with the title Introduction to VLSI Systems, and this book was something like a Bible for the developing community of VLSI designers in the world. So they introduce here new forms of internet-based multi-project chip, a new infrastructure for an internet-based MPC realization. It was possible that many students could design projects and get a rapid prototyping if their circuits are really working. With the DARPA initiative, in a very short time, more than 100 universities worldwide were working on this idea of MPC activities, and this booklet was sold in a big number of copies. This idea of an MPC technology was transferred to this Information Science Institute at the University of Southern California, and that was the start of the MOSIS project. In 1981, I started my activity at Darmstadt University, and we were very proud at that time that the university had their own semiconductor institute, and in this semiconductor institutes we were running a line for NMOS circuits, later for CMOS circuits, and for bipolar circuits. So the idea of multi-chip production design, we introduced this with a VLSI design course, and you see here on the left side a 3-inch wafer. In the middle you have the test stripes of the semiconductor technology people, and you see that we have here a similar structure of individual designs by students, and the group of students, they got very fast feedback if their circuits were operating or not. It was a big event at that time. Students came to us, to the lectures, to the laboratories. We had big graphics computers, and they had fun working on these big design machines. So for us, the MOSIS service was certainly one of the earliest and successful implementations of electronic commerce via the internet. And this MOSIS service at that time was not open to the whole world, but due to the conflict with Afghanistan, the Reagan administration limited the offering of MOSIS service to a certain number of countries. That was quite helpful for us in Germany, because we had our own technology lines, and the CAD software for designing these integrated circuits were developed by ourselves. Today, MOSIS is an established service for rapid prototyping integrated circuits. And MOSIS is still going to new directions. You have this Snugworld experience coming from companies like Facebook and Cadence and Synopsys. Here they are also involved, and on the other side they are working on advanced lithographical problems, and they also found now the interest of companies like Intel, so they have the contacts to the Intel custom foundry, and in a similar way to the MOSIS company, and they are extending now their offerings to beyond CMOS to power electronic devices, optoelectronic devices. So we see a full development of technology, and this is offered in form of design rules to the designer community. MOSIS, this is from the website of MOSIS. So you see on the left upper side 5 CMOS IC designs and a few test N and P channel MOS transistors to accept the manufacturing. And you see on the right upper side such a MPC designed wafer. And of course you can write multi-project chips, multi-project wafers consisting of a different number of unequal design circuits. As I told you, the MPC service offered by MOSIS, offered also by a European Research Institute, by the IMEC group in Leuven. They are going to new technology areas like gallium nitride ICs. So that is a technology that is quite useful for power electronics. So power supplies can also profit from circuit integration, and you can design new circuit concepts using this gallium nitride technology. In a very short time, the idea of MPCs was spreading around the world, and we see here national services in form of the Europractice service we had in Germany. The French CMP was, besides Moses and the IMEC Institute here in Grenoble, very active. We see in South America and in Far East such activities, and they are improving annually. So as we said, power semiconductors, going to integration of power semiconductors is a hot topic. We have the microsystems area with smart sensor technologies, and our chips in digital design technology get more and more complex, so we need new design and verification software. In the world, everybody is now working towards application of artificial intelligence, so machine learning and embedded AI applications are also topics investigated by the MPC services. On the other side, we see the trend that the semiconductor industry is offering small computers. You probably heard about the name Arduino, and the making of Arduino is also, wir müssten da das Bild ein bisschen höher stellen. Ja, da. Weil, ja, ja. On the other side, we see that fabricated microcomputers built on a small board with proper interfaces is a new interesting topic for many applications in industrial area, for example. And this making of Arduino was an ongoing meetup. Its origin was created in the town of Revere in northern Italy. In 1002, King Arduino became the ruler of the country, and in the bar di Re Arduino, the 5 people you are seeing here, the 5 friends, were engaged in the engineering of small circuit boards, and these small circuit boards were taking the do-it-yourself world by storm. And the historical meetup was given at a maker fair in New York City in 2005. So the main advocate of these 5 people was Massimo Banzi. We can call him the advocate of this new industrial revolution, and it was a starting point for the maker movement, and he was one of the founders of this Arduino project. We see today that at many university places, the university is offering its students a fab lab, a so-called fab lab. The initial first one was worked out in Italy, and in this fab lab, students, anybody can come and realize on a circuit board his ideas, putting it together with an Arduino device and going to interesting applications. Such interesting applications were presented or are presented on so-called maker fairs, like this maker fair in 2013 in Rome, where typically before Christmas young people in the order of 10 to 15,000 are coming to present their circuit ideas. So this is a detailed description what is going on such a maker fair. It's a place where inventors, innovators from all over the world can assemble. This maker fair is addressing schools and universities. Even professionals can take part and present to the interesting people their project. As an example, you see here how you can realize a quadrocopter based on such Arduino components. We have not the time to go to all details here, but it's in the hand of young people, and we see on the lower right corner how young people are really enthusiastically working out design projects based on these Arduino devices. We all suffer today, more or less worldwide, in a reduced number of students interested in studying fairly hard topics like modern electronic circuit design, system applications, and we cannot start early enough bringing these ideas in our field to the young people. So we have a so-called MINT idea, and it means MINT stands for Mathematics, Informatics, Naturwissenschaft and Technology. And such a MINT day we were holding, for example, some 6 years ago at Darmstadt University for the first time, and you see that young people who are typically from the high school level came, and it's not a business for men only but also for girls, and they designed their applications, and everybody was donated such a device, and they could take it home and go further on working out examples at their home. So behind this we have the idea that something like such a board can be used by many people, and we see here that out of this the idea of open source hardware was raised. And this open source hardware means that we have a main board with the Arduino components, and we have additional boards, and we fit them together and get interesting applications. And you see here such applications on this transparency. This idea of open source hardware can be extended to open science hardware. It means that we have many applications coming from physics, from biology, from chemistry, from many fields, and that is gathered in the term open science hardware. And we can use this hardware for scientific investigations. It's typically done by people in physics, and we can use standard lab equipment to come to interesting demonstrations for new ideas coming out of the science area. We see now many applications in the world in the field of open source hardware in science, and you see here some of the typical applications with a desktop, which is a digital biology laboratory, robots for biological work, and PCR, which is now very popular due to corona checks to copy DNA molecules, or open source imaging with going to open source magnetic resonance imaging. So there is a broad range of interesting applications for open source science hardware. On the level of practical applications, we see the rise of a Hackaday community. Hacks are examples of applications of this new fast turnaround method using standard Arduino type of components. That is now very popular since 2004, and every year you have such a super Hackaday conference, and community members can come and present the hacks and win prizes. So we need a new form of business in that field, and it was Lima Freit, as she got a prize to be as the Entrepreneur of the Year 2012, and she founded other fruit industries from her dormitory room where she studied, and she has now a big factory in Manhattan, and she is running the first supermarket for devices which you are using for your fast turnaround chip design projects. So she is a renowned person now for this open source movement. She is offering do-it-yourself electronic kits and components with the facilities of the internet. She can provide live electronic shows and demos, and can give the users a support forum, and she can offer component resources, libraries. She's offering tutorials on latest hardware platforms. So it's quite an interesting portfolio that Lima Fried is offering to this new community. You have a lot of interesting applications because we have here the features that you can build up your own smartphone with this do-it-yourself kite kit, and it means that here Arduino is not sufficient, but you have here a Snapdragon core, and you have everything available integrated and can easily be assembled by students, and they can learn how such a smartphone, the components of such a smartphone, and looking into the detailed internal features. That gives very interesting laboratories for the students. Yeah, this Hackaday community is now really creating a revolution, and the lessons learned here is that information technology has helped to shape our world, and we are with that type of Arduino components, with this idea of open source hardware, we can enter a new computing area of smart systems, and we have a lot of possibilities for instrumentation, for interconnection of systems, and introducing intelligent features in our products. So we can really say the world has changed because semiconductors have much enabled such a change, and it's interesting to see, and you see it here on this transparency, that youngsters thrive on collaborative hardware software maker culture. And of course you can nowadays buy a lot of hardware software kits, you can buy interesting journals to get involved in practical work. This idea of open source hardware has found the interest of the IEEE solid state circuits community, and they created this PICO program. And the idea of this PICO program is that with certainly a form of standardization, we can design chips not for the latest technology, but with the aid of a web browser. And the idea is that anyone, anywhere can do such a chip design through open worldwide collaboration. PICO is an abbreviation for that you have available a platform for IC design outreach, and there is a rapidly growing open source community to help to accelerate the construction of the required ecosystem. So we see that we have nowadays, with the support of the solid state circuit community, a new wave for the old idea of François Rousseau of MPCs in form of this PICO program, and it helps to build and connect to new communities to share the excitement of using IC innovation, and we can call this a democratization of our technology, going to new wave of complex global impact. So these initial solid state circuit society activities can be summarized that they started in April 2020 with a workshop which they called Democratizing IC Design. They had a big number of attendees, 970. They had a substantial number of undergraduate students, of young professionals, and this workshop also found the interest of non-solid-state circuit community people. In June 2021, they launched such a platform, and they sponsored 4 tape-out seats that are mentioned here on this transparency. The Pico Design Contest is still ongoing. They have, like in the MPC runs, they have deadlines for receiving proposals. You see that the number of proposals is quite interesting here. So we have really a rebirth of the idea of multi-project chips. And is this really a form of democratizing IC design? Yeah, it is making IC design more accessible and inclusive, and we can do a worldwide collaboration and get to visible results. Yeah, so enable IC design in your web browser for everyone, everywhere, with open collaboration is really something where this community is working too. So we have here other deadlines, and we have this Chip Ignite program to support undergraduates. So we see further runs here of open circuit IC design.
Okay, I will present you the evolution of CPU during the last 45 years, maybe 54, and I will show you that more laws and 2 equations allow to understand this evolution. I have known François Anceau for more than 40 years. I have started meeting him in the 80s in Chalmazel summer school, where we were teaching microelectronics and translating the famous Mead and Conway book. In the last period, we wrote 6 papers on computer architecture, introduction, scalar CPU, superscalar CPU, in order and out of order, and cache and virtual memory. And I also participate with him to the seminar History of Computer Science of the school Le CNAM in Paris. Okay, so we have an exponential evolution. Okay, the point is, are there some fundamental rule? It seems that Moore's law first, program execution time second, and CMOS power dissipation third allow to explain most of the evolution. The program execution time can be decomposed into the product of the instruction count multiplied by the average cycle per instruction with the computing CPU and the memory CPE. Okay, that means the time during which the CPU is waiting for data, and multiplied by the cycle time. Okay, this expression can be rewritten as instruction count divided by the product of the instruction per cycle multiplied by clock frequency. The CMOS power dissipation equation tells us that we have a static power dissipation, VDD multiplied by the current leakage, and the dynamic power dissipation, which is alpha, the circuit activity, multiplied by the sigma, by the sum of all the capacitance, multiplied by VDD square, and multiplied by the clock frequency. Okay, first, Moore's law. Moore's law is very famous, okay, from the 60 to 2000 and maybe a little bit more, the number of transistors per chip has doubled every n months, starting by 12 months, then 18 months, and then 42 years, 24 months. Looking further, from 2010 to 2030, that means some prediction, continue to increase, and you have here the evolution for metal half pitch, okay, the print gate length, the physical gate length, and the N is now more than 2 years. Moore's law allows the different successive technological node, okay, from 1.5 micrometer in 1982 until 5 nanometer in 2020. There have been a lot of nodes. Okay. From one node to the next one, the gate delay is divided by 1.5, which allows for higher clock frequency, and the transistor count increase per area unit. Okay, and there are a lot of consequences. We can go from a different chip to one chip to integrate different chip into only one, to use larger on-chip memory or use more and more functionality per chip. For instance, a floating point multiplication can be included in chip when it was not possible before. Okay, but there are a lot of mismatch. Okay, all exponential have not the same increase rate. Okay, CPU clock frequency has been around 25% increase. CPU before 87 has been around 35, then 60%. DRAM bandwidth is around 20% increase. The inverse of DRAM latency increase very much smaller, and the DRAM capacity increased by 60% per year. Okay, this situation has led to the cache hierarchy that can be observed when going from the single external cache of Intel 366 to one external cache for the Pentium. Then the L1 and L2 cache are on chip for Pentium 4. For Power 6, L1 and L2 are on chip, L3 is outside, and for the Power 8, we have L1, L2 and L3 on chip, and only L4 is outside the chip. How to improve frequency? You can use instruction count, instruction per cycle, or frequency. First, the simple way is to increase the frequency. Okay, as the gate delay is divided by 1.4, you can use higher clock frequency and you increase performance. But increasing performance increases also power and power density, according to the CMOS power dissipation equation. And that leads to the famous Etiemble slide that shows that going from one node to the next one, the power density increase, okay, and until the sun surface in far future, okay. And so it means that clock frequency in 2022 is limited to the 5 to 6 gigahertz range, while today technology would allow maybe hundreds of gigahertz clock frequency. Okay, it means that the problem is to get the chip without too much power dissipation and to have the typical packaging that are used today. Otherwise, you would need water cooling or maybe more sophisticated cooling procedure. Improving performance can be obtained by increasing the instruction per cycle. Okay, and in Scala CPU had IPC lower than 1 using pipeline or super pipeline. Super Scala CPU have IPC greater than 1, either with in order or out of order CPU. Very long instruction word CPU have also IPC greater than 1. But there are two aspects. First one, there are intrinsic limits of the instruction level parallelism that you can extract from a sequential program. Second point, hardware diminishing return. Okay, if you consider the right part of the slide, what is the evolution of out-of-order mechanism in Pentium and Intel CPU from Pentium Pro to Ashwell. Okay, there are two types of renaming, either by Rob or by register renaming. The amount of hardware resource considerably increase. Look at the exponential scale, okay, but the instruction bandwidth only grows from 3 to 4 microops per clock, okay, which is not very significant. Second way to improve performance is to reduce the instruction count, okay. In monoprocessor CPU, it's correspond to data parallelism, to exploiting data parallelism. First aspect, in CPU, single instruction multiple word use as several data per instruction, which means that each instruction process more data, so reducing the number of instructions that is needed. Okay, GPU is similar with single instruction multiple thread approach, okay, which means that in one instruction execute data into several threads, which is quite similar to the SAMD approach by reducing the number of instructions to process the given number of data. So, second aspect to reduce instruction count is to use data or thread parallelism parallel architecture. Okay, when you dispatch instruction among several CPU or several core, you reduce the number of instruction to execute because of the dispatching of the total amount of instruction to execute. Okay, in some architecture, communication time will be included, but either with OpenMP or pre-thread with multiprocessor or with MPI with multi-computers, parallel execution reduce the number of instructions executed per each core or each processor. So, switching from sequential to parallel programming was limited to server and supercomputer during a large period, which is called lunch period. Okay, this is the illustration of free lunch by Intel. Okay, you consider the evolution of performance between 86 and 2003, 17 years. 200 increase in clock frequency, okay, 200 increase in number of transistor and 11 in the gauge length, and 1000 increase in performance according to the spec in 2000 benchmark. So, why did we go from monoprocessor to multi-core? It corresponds to a performance power trade-off. Okay. We have mentioned the intrinsic limitation of monoprocessor, even multi-threaded, and so the need to go to single core to multi-core is illustrated by the right part of the slide. So here we consider that the power is proportional to the area, and the single thread performance is proportional to square root of the area. So a small core has performance 1 and power 1. A large core, 4 times bigger, has performance which is double, but power is multiplied by 4. And if you look at the 4 core, okay, the performance is multiplied by 4 when the power is multiplied by 4, which means it's exactly the same ratio as the small core. And so this leads to the multiprocessor, which is 2 CPU in a single chip, or multi-core, 2 CPU in different chip and multi-core, which is several core in the single chip. So multi-thread CPU is another way to reduce the instruction count, either for sequential program or multi-programming or for several threads. Okay. So there are two aspects: is fine-grained multi-threading. So in that case, you switch in one clock from one set to the next one on pipeline hazard. And for instance, Sun Niagara or Oracle servers use that approach. Second approach is simultaneous multi-threading, where you issue instruction for different thread at each clock, either with Intel hyper-threading with 2 and IBM Power from 2 to 8 thread per clock. Okay, so second aspect is that multi-threading reduces CPU mem as you switch from one thread to another one when there is some cache stall and some or memory weight. Okay, so you can mix multi-core with multi-threaded core. Let's go to power dissipation. Okay. First point, reducing power dissipation. There is one observation is that with the successive node, okay, the static power dissipation increase versus the dynamic power dissipation. And you have to take care of that issue by different technique. One technique is at the technology level. Intel Trigate is a good example where you reduce the leakage by one order of magnitude by going from the planar implementation to the Trigate implementation. So, second aspect is you can use circuitry, for instance, using virtual VSS in the L3 cache of Xeon CPU. Okay, first, the active mode is the virtual VSS is 0 volt. Then you have a step mode when you reduce the power leakage by 2, and the shut-off mode when you reduce the power leakage again by 2. That's been by 4, corresponding to the first situation. There are other techniques to reduce power dissipation. One technique is to integrate several operating modes per block. For instance, in the 5th generation Intel Core, you will find 4 different working modes. Working, G0, sleeping, G1, G2, soft off, and G3, mechanical off, and several subgroup. Okay. Some other technique consists in dividing a chip into several domains. Okay? All the transistors don't need the same power supply, for instance, so you can divide the chip into different power domains by using the VDD that is needed for the different part. You can also divide the power supply, the chip into several clock domains. What about future? Okay, it's clear that Moore's law is going to an end, even it's very difficult to predict precisely when. Okay, Moore's law will finish someday. The point is, when is this day? So, because there are some fundamental limits. Okay, execution time. Okay. There will not be significant change in clock frequency because of the power dissipation issue, either for packaging or for the chip working correctly. There are limits of instruction level parallelism in core, so it's difficult to predict a big increase. Okay. New processing in memory architecture can tackle the issue of the memory wall, c'est-à-dire when you reduce the gap between the processor speed and the data access time, you will increase the instruction per count. The instruction count continue to decrease. Okay? For instance, Etiemble with do more job per instruction, 256, 512, and new data size such as 16-bit floating point or 8-bit floating point also reduced the number of instruction because more data is processed per instruction. New two-dimensional instructions are used in tensor core of NVIDIA or matrix multiplication unit of Google TPU. More core is more doubtful because going from multi-core to many-core raises a lot of issues such as cache coherency and the way to access successfully to data. Power dissipation, okay, as long as CMOS is there, as long it will be used, this equation will be there. Concluding remark, I have presented the main trends, not the detail of CPU evolution, and they can be explained by the Moore law, the execution time equation, and the power dissipation equation. This is valid for software programmable processor as long as the currently used technology will be used. Okay. Evolution of CPU is driven by new specific application, artificial intelligence, Internet of Things, and so on. Business as usual, that means the fight between ARM and RISC-V, proprietary versus open source, is well known. Okay, that's all. Thank you for your attention.